So accuracy is how close a measurement is to the correct measurement. So let's say that in this glass there are 147 milliliters, and I record that as 146.92548. Okay, that would be a recording of the accuracy of my experiment. I am only zero point 0.1 off from the correct measurement. So that would be a somewhat accurate measurement of my experiment. Whereas the precision would be the level of exactness of my measurement. So let's say I have 147 milliliters of water in here, and I take 10 measurements of the amount of water in here, and I have a good grouping of my measurement every time. Every time I get 146.9, 146.8, 146.9, 146.8, 146.9. That would be a precise experiment because I am getting close to the same level of measurement every time. I'm exact in my measurement, whereas the accuracy is measuring how close I am to the actual quantity in here. So I think of accuracy as, did you do a good job in reaching your target or reaching your goal, whereas the precision is how exact is your instrument, and did you measure in a precise manner, or did you measure in a correct manner that resulted in a good grouping of your trials. And I think it's a little bit easier when we look at this diagram over on the right. So on the bottom, on the x-axis here, we have the measurement of the accuracy. On the y-axis, we have the measurement of the precision. So as you move to the right, you increase accuracy. As you move up, you increase precision. So let's start here on the bottom right. So when we're shooting at a target, or you're shooting at a bullseye, your goal is to hit the center. The center is the perfect score. So in this case, in the bottom right target, we see that we have X marks a spot in the middle. That's our goal. We want to hit that point. And we have all of these dots or shots we've taken around the target that are close to the middle, close to the bullseye, but they're not on the bullseye, and all of the shots are also in a different location. So we would say that this has a high accuracy because every time we're getting somewhat close to our desired actual outcome. However, the experiment we're doing here on the bottom right has low precision because every shot is in a different location. So the grouping of my measurement is different every time. Now let's move to the one on the bottom left here. This one has low accuracy and low precision. Again, the goal is to hit the bullseye in the middle. None of my shots are around the bullseye, and none of them are in the same location. So I have low accuracy and low precision. Nothing hit the target, and I was bad at doing my job and measuring, and I didn't get any good groupings. Now let's move to the top left. In this one I have high precision but low accuracy. Again, the goal is to hit the bullseye. None of my shots are near the bullseye. However, all of my shots are grouped on top of each other. So every time I took a shot, it reached the same area. So I have high precision because the exactness of my measurement or the exactness of my shot was very similar every time. It was off by a small proportion. However, it was low accuracy because I was not able to hit the bullseye, my desired outcome. Now let's look at the one at the top right. Again, the goal is to hit the bullseye right in the middle. And in this one, you see that every shot is on the bullseye and every shot is in a similar grouping, is in a similar position. So in this one, we have high accuracy because everything hit the bullseye, which is the correct measurement or the correct outcome. We want to get the highest points possible. And then it's also high precision because all of the shots ended up there in a good cluster together. So that's accuracy versus precision. And we use accuracy and precision to talk about the error or to account for the error in our measurements. Now, to track these imperfections and this imprecision, we use what we call significant figures. So a significant figure is basically the number of certain measurements that you have, or the number of certain digits you have for a measurement, and then also one uncertain digit for a measurement. So let's say I have a thermometer, and this thermometer reads in 1 degree increments, okay? And I read this thermometer out, I'm boiling water, and it's reading 100 degrees Celsius. 100 degrees Celsius would be the number of certain digits. Okay, and then technically, according to significant figures, I would need to add one additional uncertain digit to that. So you look at the line on your thermometer and you would say, okay, is that line slightly above 100 or slightly below 100? And then based off of that reading, you would add and say maybe the actual reading according to significant figures is 99.9 degrees Celsius, or maybe it's slightly above, and I would say that it's 100.1 degrees Celsius. So you have to record what is exact according to your instrument. So for example, on a thermometer that reads in 1 degree Celsius increments, that would be the 100 degrees would be my certain digits, and then I have to add one additional uncertain digit, which would be my 0.1 degrees Celsius, to say that I am tracking the imprecision or the imperfections in my measurements. Now, these significant figures can be kind of hard to understand, so we've created some basic rules for them. And again, the significant figures are the number of certain digits in your measurement plus one uncertain or one estimated digit. So let's look at this number over here on the right. So if I wrote the number 0.0560 and we said that was the number from an experiment, let's say I'm measuring the length of something. So this is in picometers, millimeters or something. We would write this 0 just to the left of the decimal, just because that would make it look nice. That number is going to look cleaner if I put that 0 there instead of starting with a decimal. So that one is not a significant figure. And then I write my decimal, and then to the right of there I have a 0. This 0 is also not a significant figure. It is a requirement to write the number correctly, because if I wrote 0.560 versus 0.0560, that 0 is still critical to the structure of this number, so it has to be there, but it is not significant. Now once I get to the 5, that is my first significant figure. This is a number that has true meaning and value as the measurement of this experiment. The 6 is my second significant figure. Again, it has true meaning and value to whatever it is that we're measuring. And then the last would be the 0. That's my third significant figure. So this would be the one that I potentially estimated or measured the uncertainty of in my measurement. And again, we have some basic rules to help us understand these. So the first situation would be, do we keep the 0? So like, for example, this number on the right, 0.0560 that we were just talking about. There's 3 zeros that potentially could be significant or not significant here, depending on the situation. So we have rules for this. So do we need to keep the zeros? The first situation would be if I have a 0 between other non-zero digits, they are significant. So let's say I recorded the time it takes somebody to run from one side of the room to the other, and it came out to 4.015 seconds. In this case, that 0 is sandwiched in between a 4 and a 1. So I can't get rid of that 0. It has to stay there, or the integrity of the number itself changes. So in that case, that 0 is significant. So that number has 4 significant figures: the 4, the 0, the 1, and the 5. The second situation is if I have a 0 in front of non-zero digits, then it is not significant. So just like right here for this 0.0560, these first 2 zeros are not significant, and that is because it is a 0 in front of non-zero digits. So they're not really important. However, that 0 after the decimal is providing value in some way. It's just not significant. It's integral to the structure of the number itself. So in our example here, we have 0.007 seconds. In this case, we have 3 zeros that come before a non-zero digit. So those zeros are not significant, and we only have one significant figure here in this answer. The next situation is that if we have zeros that are at the end of a number and right of the decimal, they are significant. So let's say that I have these 2 significant figures, 5, 7, and then I have a decimal, 00 grams, so 57.00 grams. Because of the structure of this number, just like with this 0.0560, where this 0 after the 5 and the 6 are significant, with this 57.00 grams, the zeros after the 5 and the 7 again are significant in this situation, just because of how they're set up. Because they come after the 5 and the 7, they are adding value to that number, and therefore they are significant. So here we have 4 significant figures. The next one is that zeros at the end of a number but to the left of a decimal are significant if they were measured or estimated. So this is a rule that can go either way depending on who you're discussing this rule with or who's teaching your class. In my case, I am going to look at this number on the right here. It says 10 meters. This could either be one significant figure or two significant figures. In our case, we are going to count this as two significant figures because based on rule number 3 here, that zeros that are at the end of a number and right of the decimal are significant, we're going to follow a similar rule here, and we're going to say that even though this 0 is not to the right of a decimal, it is still significant. It's still providing value. The reason this one could be one or two significant figures is because we could rewrite this number 10 meters as 1 times 10 to the first in scientific notation, and in that case it would always be one significant figure. However, I am not going to require that as for you, so in this case we are going to count this as two significant figures. This next one is about when we start to do math or arithmetic with numbers that have significant figures. So let's say we are adding or subtracting two numbers. We're going to say that when we add or subtract, we're going to round the final answer to the first column of the left containing an estimated digit. So just based on the way that we do math, let's say we take the number 94.22. We have 4 numbers there, which means we have 4 positions in that number. And then we're adding it to 5.52. We have 3 numbers there, so we have 3 positions there that'll be overlapped, and we have 1 number that doesn't have a buddy, basically. So what we do in this case, we draw a line at that 3 position and we cut off this 9 here. That's how you can think of it. And so the correct number of significant figures to report for this type of number would be 3. Okay, so that's just a simple way of saying, because we add and subtract in columns, or that's how you should be thinking of it, is adding and subtracting in columns, you basically are going to report the lowest amount of significant figures that contain an estimated digit. So 94.22 plus 5.52 would equal 99.74. However, because 5.52 only has 3 significant figures, you can only report 3 significant figures, so therefore we would report 99.7, which would have 3 sig figs. And then lastly, we have multiplication and division. So for multiplication and division, we're going to have the same number of sig figs as the number with the smallest sig figs. So let's say I take 114 times 5.22, and that would equal 595.08. That has 5 sig figs, okay, but my inputs there, 114 has 3 sig figs, and then 5.22 has 3 sig figs. So I can't report 595.08, so I would cut off, just chop off the 0.08, and I would report it as 595 with 3 significant figures. Now lastly, as I said earlier, one of the things about sig figs is there's some situations where we just can't talk about the numbers properly or can't report the correct number of sig figs because we'll end up with too many zeros, and those zeros will end up being counted as significant just based on their position. So in those situations, what we do is convert the number to scientific notation, and this is how we can talk about huge quantities like the speed of light or the number of atoms in a substance or in an element. And so this is a way that we can make our calculations easier. And to do this, basically we take the first part, which will be a number between 1 and 10, and then the second part will be 10 times the power of some number. So if we look at this example on the right, this is 3 and an 8 with 1, 2, 3, 4, 5, 6, 7 zeros behind it. So in this case, the numbers that are actually significant here that are providing us value are the 3 and the 8. So we could take and draw a decimal point to the right of this 0 and then slide this decimal over until we only have the 3 and the 8 left. So that would be 1, 2, 3, 4, 5, 6, 7, and 8. And then we would write 3.8 times 10 to the 8th. And that's how we would report that number and convert it to scientific notation. So we'll do this many times throughout the semester, especially once we start to talk about moles of substances. And you'll have to do math on the number of moles of a substance that is found in your reaction or whatever the situation may be. So it's important that you understand the basic structure of scientific notation. All right, and then lastly, let's talk about specific heat. So we talked about specific heat in our last lesson, and basically we talked about the fact that we were going to set up a coffee cup calorimeter and then be able to calculate the specific heat of a metal based on the quantity of heat that it took to raise a unit of mass of a homogeneous material by 1 degree Celsius. Okay, and the equation to do this is down here on the bottom left. Basically, we have heat, which we measure in joules, so that will be represented by Q, and Q will be equal to M, which is the mass of our substance, times C, which is the specific heat in joules per gram degree Celsius, times the change in temperature. Okay, so we'll use this formula, and when we do our coffee cup calorimeter, we're going to measure the amount of heat that is gained by the water, and then use that to be equal to the amount of heat that was lost or gained by our metal that we're testing, and then we'll set those formulas equal to each other. So let's just do a simple example here on how to calculate specific heat, because you'll need to be able to do this for your lab. So let's say we have 1 gram of iron, and it is at 100 degrees Celsius, and then we take that iron and we cool it to 50 degrees Celsius, and it transfers 22.5 joules of energy to the surroundings. We need to calculate the specific heat of this metal. So we're going to say that we have C of P, which is equal to Q divided by M times delta T. Basically all this equation is on the left is the equation on the right, but what we did is took and multiplied over the delta T, and we divided over, but all we did was divide over the mass and the delta T, so that we ended up solving for the specific heat. So we're looking for specific heat here. And in this case, C of P is the specific heat at a given pressure, so we're assuming that the iron is a consistent pressure and volume. The mass, the M, is the mass of our substance, which is given to us 1 gram of iron. And then the delta T is the change in the temperature from the final to the initial position. So in our case, our C of P would be equal to Q divided by M times delta T. So M is equal to 1 gram, that's given here up here, and then delta T is going to be the final temperature minus the initial temperature. So our final temperature is 50 degrees Celsius because it was cooled. The iron was cooled to that temperature, and the initial temperature was 100 degrees Celsius. So that is 50 minus 100, which would be minus 50 degrees Celsius. And so that'd be 1 gram times negative 50, which would just be negative 50. And then our transfer of energy was 22.5 joules of energy to the surrounding. So 22.5 divided by 50 would be our official problem there. And 22.5 divided by 50 is 0.45. So the specific heat of this iron, this 1 gram of iron, is 0.45 joules per gram degrees Celsius. Okay, and that is what you're going to have to do for your experiment today. That's all I had for you guys. If you have any questions, please feel free to leave a comment below or ask me in class. Thank you for your time, your energy, your effort, and I'll see you next time.